Welcome. In this session, we'll define a second-order condition for a stationary point to be a minimizer, and we'll look at some of the eigenvalues of a Hessian matrix, and we'll go through some examples. Let's begin by recalling from the previous session and earlier sessions what happens in scalar land. A sufficient condition for a stationary point to be a minimizer was that the second derivative at that stationary point had to be strictly greater than 0. And what we had for a stationary point was that the directional derivative, so for a function that has a scalar, has a vector argument and produces a real level, the necessary condition was that the directional derivative in direction v of a function had to equal 0. And the way that we looked at that was we said that for all vectors in the vector space that we're looking at, that if the vector was non-zero, then the derivative in that direction at that W star had to be equal to 0. Now, that was our necessary condition. To get our sufficient condition, what we can do is we can reason further like this. So what we'll say, sufficient, is that if for any vector, so any vector direction, what we'll say is that if the vector is not the 0 vector, then what do we mean by convex, or what do we mean by the second derivative is greater than 0? Well, the extension from scalars into vectors is that the quadratic form of the Hessian at that point has to be positive. And we can write that as saying the product, if we take this vector and transpose it, and then we write the Hessian at W star, and we're writing that as the grad squared of f evaluated at W star. So that's a matrix, and if we then multiply that by the vector, this is the quadratic form of the Hessian at that point in direction v, and we want that to be strictly greater than 0. And if all of that is true, then a stationary point W star is a local minimizer, and that is sufficient. With this understanding, let's go to some computer examples where we can recall some material from prerequisite courses, and we can then unify that into some understandings of the Hessian matrix. Let's recall from previous courses some of the relationships of eigenvalues of a symmetric matrix to these quadratic forms. So let's represent any matrix B as a symmetric matrix that has real entries and is square. Let's recall that a positive definite matrix, we wrote that as the predecessor symbol. A positive definite matrix was one that has a quadratic form with any non-zero v that's strictly greater than 0. And using eigenvalues, an equivalent statement was every eigenvalue is strictly greater than 0. We said a matrix was positive semi-definite if the quadratic form was non-negative, and in terms of eigenvalues, that meant that every eigenvalue was greater than or possibly equal to 0, and that's where the semi-definite part came in. We had likewise definitions for negative definite and negative semi-definite, and we referred to a matrix in prerequisite courses as indefinite when none of these conditions applied. And in particular, what that means is that there is at least one eigenvalue that is strictly positive and at least one eigenvalue that is strictly negative. And those are part of being an indefinite matrix. So now let's take a look at what this implies for the Hessian matrix. Suppose that we're at a stationary point. What we can say is if the matrix is positive definite, then this is a strict local minimizer. It may not be a global minimizer, but it's a strict local minimizer. If the matrix is negative definite, then it's a strict local maximizer. One of the things we can say if it's indefinite is that it's a saddle point. A problem is if the matrix is semi-definite, whether it's positive semi-definite or negative semi-definite. It could be any of the above. It might be a local minimizer. It might be a local maximizer. So a problem mathematically is that when a Hessian matrix has a 0 eigenvalue, it's really difficult. It can be quite difficult to figure out whether it's a minimizer, a maximizer, or a saddle point. Let's take an example of a Hessian matrix that is positive definite. So that means that both eigenvalues, we'll look at 2 by 2 examples. Both eigenvalues are positive. One example is a paraboloid. Here, it's a surface of revolution, so I've taken a parabola and I've spun it around the axis, and this is what I get. And the function is convex. It's pointing upward in any direction when we're at the stationary point. So in this case, there's only one stationary point for the function, and no matter what direction we go, that is pointing upward. Let's take a look at a 2D positive here I'm picking an indefinite. So here we have one eigenvalue that's positive and one eigenvalue that's negative. An example is a saddle function. Mathematically, this one is referred to as a hyperbolic paraboloid. We'll call it a saddle because it looks sort of like a saddle. The purpose of a saddle is to constrain, let's say that this is the head of a horse and this is the tail of a horse. What it does is it constrains a rider between the head and the tail, and then it constrains the rider's legs, and so it's referred to as a saddle function. Here, there's only one stationary point for the whole function. It's at this location, and if I go in some directions, it goes upward, and if I go in other directions, it goes downward. And that's the geometry that corresponds to an indefinite surface. Now let's look at a positive semi-definite function. So that would be, in a 2D case, it's got one positive eigenvalue and one 0 eigenvalue. An example of that is a paraboloid sheet. And if we plot it in a particular way in MATLAB, it looks sort of like a taco shell. So we'll call that the taco function. Here, there's an infinite number of stationary points, and they're all along the minimum or the valley. Each of these is a local minimizer, and there is no strict local minimizer to this function. So there's an infinite number of local minimizers, there's an infinite number of global minimizers, but there are no strict local or strict global minimizers to this function. Now, let's take a function where the Hessian matrix has all 0 eigenvalues. Can this happen? Well, yes, it turns out it can. I'm going to pick a function that is not flat, and has one stationary point, and at that stationary point, both eigenvalues are 0. This is sometimes referred to as a monkey saddle function. Here, there are 3 places going down, and you can imagine for a monkey that there are 2 legs and a tail that all have to be constrained. And so for a monkey saddle, at that stationary point, there are some places where it's going up, some where it's going down, some where it's absolutely flat, and it's actually a little bit complicated to figure out what's going on in this function. One way that I personally look at things is with slices. If you've taken a course from me already, you know that when I see a square matrix, I want to know what its eigenvalues are, and I also want to know what its eigenvectors are. And a Hessian matrix, especially a 2 by 2, has eigenvectors that are easily calculated, and those vectors are directions. And you can imagine that what we do is we're now going to say in that vector direction, we're going to have a magnitude, and we're going to let that magnitude be 0, be positive, but we could let it be negative. That is, it could just be a scalar multiple of that vector. So what happens when we take a point and we constrain it along an eigenvector, and we want to then, so that'll, each time we evaluate it, it gives us a point, gives us a 2D vector, and we can evaluate that and we get a level. So what do those look like? Well, those are slices of the geometries. So if we recall that bowl function, it was a paraboloid of revolution. If we take the 2 eigenvectors, they're orthogonal, right? And in those orthogonal directions, we get the same picture. That is, these are now ways that we can visualize the function along the eigenvectors of the Hessian matrix at that stationary point. Well, let's try this for some of the others. Let's take the positive semi-definite, which was our taco function. If we do this, what we see is if we go along one eigenvector, it's dead flat, perfectly flat, which is the valley. And then if we go perpendicular, we get the paraboloid. And so we can use the eigenvectors at any stationary point of this function to understand some of the local geometry. It's not giving us the global geometry, but it's giving us the local geometry. Now let's take that indefinite case, which was the saddle function. Here, one eigenvector is describing the downward shape, and one eigenvector is describing the upward shape. So this is demonstrating the local non-convexity of the function. What happens if we take that monkey saddle function that had zeros for the eigenvalues? Well, that doesn't mean it has 0 eigenvectors. And when we do the eigenvector decomposition, what we see is that in one direction, it's locally completely flat, and in another direction, it's a cubic. This is one of the examples of why when zeros are eigenvalues of a Hessian matrix, the matrix, even in a 2 by 2 case, can be quite complicated to analyze. So, in summary, what we've done is we've extended the concept of stationarity from scalar land to vector land. We've extended the idea of a second derivative to the vector domain. We're writing that as the grad squared f, and we're calling that the Hessian matrix. It's a one necessary condition for a minimizer is that a point be stationary, and a sufficient condition is that it's a stationary point with a Hessian matrix that is positive definite at that stationary point. Saddle points require a complicated analysis.